Hello and welcome to my presentation, where today I'll be talking to you about path planning algorithms. There are many different algorithms that a number of robots use, but today I'll be sectioning it into two. One section will be grid-based algorithms, and the other section will be sampling-based algorithms. There's many different famous grid-based algorithms out there. The most famous one maybe being A-star, but other ones are also hybrid A-star, D-star, and theta star. The A-star algorithm is great to use depending on your situation. It converts the area into a grid or graph, thus making it a grid-based algorithm. It is also considered a complete algorithm, meaning if there is a solution available, for example, if a robot is actually able to reach the end of a maze, it is guaranteed to find it. It is also optimal, which means it will find the shortest path possible to the goal, and for this example, to the end of the maze. It builds upon Dijkstra's algorithm, if you're familiar with that. It is also a heuristic-based algorithm, which essentially means the algorithm makes educated guesses, and I'll explain that in a moment. The issue with this algorithm is that it is very expensive, since it is a lot of calculations that has to be done, and that's why it's not the best for really large spaces. So there's a great video by Sebastian Lagu. I put the link for the video under the presentation, and he explains A-star algorithm very well using visuals, and I've taken a screenshot from that video to explain this presentation as well. And to start, this is point A and this is point B, and the first thing that you have to know is what is the distance for one unit. So it's safe to say that moving one unit is 1, and using Pythagoras theory, you can say that moving diagonally is the square root of 2, which is 1.4, and then you multiply by 10 just to give you a nice integer value. So you can see that the top left number is the g cost, and that is the number or the distance between the starting node. As you can see here, 10, diagonal 14, and then the top right number is the h cost, which is the heuristic, as I said before, the educated guess number, which is the distance to point B. As you can see here is 28, so as then you move 2 times diagonally, which is 28. So first you find out your numbers for all the boxes around you, and again you add up your g cost and your h cost, which gets you your number here. As you can see, the lowest number is 42, which means you go up to 42 here, and then again you calculate the distance around you, find the lowest number, this is 42, and then you go again, find the lowest number, which is 42 here. As you can see, the h cost here is getting lower and lower, which means getting closer to the goal. And as you can see here, you reach the goal in 4 moves. Of course, it's not always going to be as easy as that, as there might be an obstacle in the way from your end goal. But nonetheless, A-star algorithm still finds you the most optimal path and the most shortest path possible. But from this video, I've taken another screenshot just to visually show you how much calculations goes into getting from here, which is point A, to point B. Almost all the cells in the area are being calculated, and you can imagine with a bigger play field how expensive that can be. So something to keep in mind Depending on your project or your situation, it is a very expensive algorithm to use. Now I'll go over sampling-based algorithms that operate a bit differently than grid-based algorithms. Some of the most famous ones being RRT, which stands for Rapidly Exploring Random Tree. There's also RRT star. Also PRM, which stands for Probabilistic Roadmap. And also FMT, which is Fast Marching Tree. The RRT algorithm is much more different than A star, in which no sense of a grid-like structure is used. It uses a method called random sampling, which means it constantly chooses a spot on the map that can either be random or have some sort of bias towards more unexplored areas, and I'll explain that in a bit. It is very useful for situations where your robot has to maneuver around complex obstacles, and it's also useful when you want your robot to plan out its path in real time. For example, if your robot is prone to being blocked suddenly. It is complete but not optimal, which means it will guarantee you a path to take to the finish, but it might not be the most optimal or the shortest. This drawback comes with a positive, which is that it is not as expensive as a grid-based solution like A star. So it is best to use sampling-based algorithms for situations where you just want a valid path, but don't really care about if it's the fastest way possible or not. There's another great video by MATLAB. I put the link in the bottom of the presentation. And I've taken a screenshot of this high-level visualization of the RRT algorithm. And I just want to direct you to this start, and this is the goal. And the random sampling part comes in where new nodes are being created randomly anywhere in the area. For example, here a new node was created, and then it gets connected to the nearest node. For example, here it gets connected to start. Here it gets connected to here. And there are some rules that follow. Usually there is a maximum distance that a node can be from the previous node or the closest node. Also, if there is an obstacle in between the two nodes, it is not considered. So as you can see here, this path over here and this path over here, you can see just from these two branches, how all this area is being explored. Thus the name Rapidly Exploring Random Tree. And also you can see here in the back, there is nodes being created here as well, but it's generally not considered since it is farther away from the goal. So new nodes are being created constantly and randomly, as you can see here. A new node is here, gets connected here, new node is here, gets connected here, and it keeps happening until it reaches the goal, and then it gives you the path. And I just want to show you the difference between A star and this algorithm is that it is done in a shorter path or in a shorter amount of calculations, but the path is not as optimal. As you can see, it's very zigzaggy, but it is a lot faster to know where the goal is and the path to it. So here is a GIF on the RT algorithm, in which this is the start and this is the finish. And you can see how in the beginning random nodes are being placed, and it becomes they search the unexplored areas of the map, and eventually, I believe in this representation, it's more biased towards being closer to the goal. And also in this representation, there's a smoothing out algorithm to make the line more smoother. But I want to visually show you the difference between the grid-based solution, which was the A-star, and how much less computational power it takes to use a sampling-based algorithm like this one. While it might not be the best path, nonetheless, it is a valid path. So something to think about, depending on the situation, again, which solution you want to use. Thank you so much. This has been my presentation on path planning algorithms. We talked about many different types that there are. We talked about grid-based algorithms, sampling-based algorithms, the computational differences between them, and the intricacies within those algorithms. And I hope you enjoyed, and thank you.